Hello, my name is Sangmin Kim, and I'm currently working for Samsung Electronics. Today, I will present a poster, and the title is System-Level Power Estimation of SSDs under Real Workloads Using Emulation. I will first introduce the motivation behind this work, and then describe the verification methodology and the proposed SSD power estimation methodology. Due to the demand for faster data transfer speed requirements, the performance of SSDs is currently increasing. Our recently released SSD from our company supports the PCIe 5.0 protocol and has a sequential read speed of 13,000 megabytes per second. These higher performance SSDs often result in higher power consumption, which is why accurate power estimation of SSDs has recently become important. In our work, the main objective was to estimate the power of SSDs under real workloads. So this is a figure of the components of an SSD. An SSD consists of a controller, which is an SoC, a NAND, which is used as a memory storage device, and a DRAM, which is used as cache. We will present a methodology to estimate each component separately, and then combine these estimates to obtain the SSD power. Power estimation is performed for realistic I/O usage scenarios. So we will now describe our verification requirements and environment used. We need to handle SSD controllers with a design size of tens of millions of instances. We also need to support the usage of firmware. The simulation time needs to be relatively long since peak power can occur only on corner cases, which would be hard to discover with short simulation time. Our solution is to use an emulation-based hardware software co-verification environment, which we also represent using this figure. We accelerate our UVM environment using emulation. This figure is an overview of our SSD system level power estimation. We estimate the power of NAND, DRAM, and controller separately to obtain the SSD power. To accurately estimate power, we obtain silicon measurements for DRAM and NAND commands and use these power values. We create command information dumps and convert the command information into power values. And for the controller power, we use a standard SoC power estimation flow. To obtain the command information, we modify the behavior models of the memory subsystems to dump internal status register value changes. This allows us to know what command each component is executing, whether it is tprog or tr for an AND, or if a DRAM is running a pre-charge or activate command. We use this info to calculate power using the previously mentioned silicon measured command power values. So this figure shows an example of a one-channel, two-way NAND configuration. We can see that by looking at the dump log, we can check which command each way is running and also the length of each command. For experimental results, we estimated the power of a commercial SSD and compared our estimates with actual silicon measured power. We used the identical product firmware during estimation and measurement so that the difference in firmware operation does not cause estimation errors. This table shows the estimate error of each component and total power for each scenario tested. We test 4 scenarios: sequential read-write and random read-write I/O operations. For average power, the maximum error is 5%, and for peak power, the maximum error is 8%. Since the peak power corner case could sometimes be not covered during simulation, the error of peak power is larger. So in this research, we use silicon measured command power to estimate the memory subsystems of an SSD. We obtain the command info and timing by modifying the memory behavior models. Emulation is used to accelerate the verification time. Results show that the average and peak power was estimated with a maximum error of 8%. Thank you.